Okay, I think we can begin our webinar. I just greet all of you and welcome you. I am pleased and honored to welcome today Rémy Bossuon as part of this baby webinar. Rémy Bossuon is not someone unknown for you because many of you have been I've had the chance to listen to Rémy Bossuon for few months, and when he presented his activity at SCOR. Rémy Bossuon is Secretary General of the European Mediterranean Seismological Center, a non-profit organization constituting one of the world's main centers of seismological information. Rémy Bossuon will present us his innovative lastquake application, which received the support of the SCOR Foundation. The project built on an existing working prototype developed by scientists over the last 20 years, one of the top 2 global prototypes in this field. Lastquake had the powerful advantage of providing information on the occurrence of earthquakes instantaneously, whatever their location around the world. It gives the profile of the incident based on individual information collected from people who connect to the application and who are asked to specify both their geographical position and the felt intensity of the earthquake. And you will see it is truly powerful. The 3-year agreement signed between the SCOR Foundation for Science and the European Mediterranean Seismological Center had the objective of completing, renewing the EMSC technical infrastructure and extending citizen seismology in order to improve the rapid assessment of the effects of earthquakes. This project is important because it makes clear how eyewitness data that are easier to gather can replace dense, real-time seismic networks for rapid impact assessment. Rémy Bossuon will illustrate the effectiveness of this application using concrete example of recent earthquake, maybe including, I don't know, the catastrophic earthquake of 7.8 intensity that occurred in the Kahramanmaraş region in Turkey, the 6th of February 2023. But please, Rémy, the floor is yours.
Thank you. And first, thank you for this invitation. First, I would like to express my big thanks on my personal and EMSC behalf for this 3 years collaboration, because as it was just explained, it was absolutely essential. We have been building this system for a number of years, but we never had the opportunity to really integrate it. So it was really the purpose of this 3 years agreement, and I think we have done, we have made significant progress since. So my talk, so basically what I would like you to remember at the end of the talk is that citizen seismology, and I will explain what it is, can contribute to risk reduction, seismic risk reduction in 2 different ways. First, is by improving crisis and risk communication. And secondly, by improving rapid impact assessment, which is key for the efficiency of the response of an earthquake. So I will have 3 parts in my talk. First, I will explain what citizen seismology is, how the lastquake system works. Then second part will focus on the risk and crisis communication, and the last one will be on the impact assessment. So what is citizen seismology? Citizen seismology is part of what is called citizen science. So that's when you involve citizens in science. So in this case, we involve citizens for collecting data. And basically, citizen science has become easier to do since the inception of the internet, and in our case, really that's the smartphones which makes the big changes. And we may have forgotten about this, but smartphones are not that old. Here are two pictures that I love. That's the two last election of Pope in Rome. So if you have the same audience, same location, and you see in 2005, there was no screens, no smartphones. A few years later, there were smartphones everywhere. So this is a real revolution. And what we have been doing is taking advantage of this. These smartphones are with us all the time, 24/7 a day. So they are with us in all compartments of our lives, including the emergencies. So some argues that smartphones have modified the way we behave. I will rather argue that smartphones, the big difference is that now we have technology at hands, but as soon as the technology is available, it is used. So this is a very iconic picture that all seismologists around the world will know. It is the fire which followed the San Francisco earthquake in 1906. And you see it is two young ladies being taken in picture in front of the fire. So there were not many cameras at the time, but you already had exactly this type of things. What will happen today if you had the same event? We will have hundreds of thousands of such pictures on the social network. So that's the scale which has changed, but basically as soon as the technology becomes available, it is being used. The whole idea of our system started in 2006. Simply because when there was a felt earthquake, so as it was explained by Philippe Trainard, we provide rapid earthquake information, and we realized that every time there was a widely felt earthquake, there was our servers were crashing simply because there were too many people. So basically, if you look at the top left, the blue curve represents the time evolution of the number of people hitting our website following an earthquake, in this case of 5.3. And you see there is a very large increase immediately after the quake. It is just, that's why it just reflects the fact that people are looking for information. So you can argue that the amplitude of this peak is a measurement of the public desire for information. But in practice, how can you use it? Well, you just have to look at, so to detect the surge, then you look where the people come from using their IP addresses, so Internet Protocol address, which has a accuracy typically at city level, and you know where the earthquake is felt before you get any seismic data. The second stuff we have implemented, is what we call Twitter earthquake detection, which was first developed by the US Geological Survey. It is very similar. The idea is very similar. It is just you count the number of tweets, so the number of messages on Twitter containing the keyword earthquake. If you have an earthquake in Italy, it will be Mamma Mia terremoto a number of times. So you just count the number of tweets containing terremoto, and you have exactly the same surge. The problem with this methodology is that Twitter is not that popular, and even less today, in many countries of the world. And the geographical information is very poor. But still, if you have something in Southern California, for example, it is extremely efficient. The last thing we have been implementing is based on our smartphone app that I will present you just after. Here, this is the red curve. Look at the scale. Here, it is in seconds. And we look at the number of people opening the app. And here, this is again a felt earthquake. And you see the increase started a dozen of seconds after the quake, and we detected 20 seconds after the quake in this case. So all these type of detections, we call them crowdsourced detections. They typically occur within 15 to 90 seconds after the quake. We don't use any seismic data, and they precede the first seismic information we can have. So it is a very powerful way to detect felt earthquake. And basically, it is based on the fact that the internet acts today as the digital nervous system of our planet. So every event in the physical world can create a footprint, digital footprint on the internet. So here, what I represent, the star represents an epicenter. All the black dots represent an IP location. And it is an earthquake in Oklahoma, so the propagating circles are the seismic waves, so what the people actually feel. And every time we have, so you have the time at the bottom, so in minutes and seconds. So red dots represent localities from which we have a lot of visitors hitting our website. And the bigger the circles, the larger the number of visitors. And if you look, the first one to hit our website are closer to the epicenter. So basically, it means that here it is just with the internet, it is not the app, and still the people are real-time sensors. So they report by hitting our website or opening our app, they are basically becoming real-time motion sensor. And to prove it, we had a paper a few years ago. We just took the website traffic on our website, following 2 minutes following an earthquake in Virginia in the US, and we just retro-propagated the hit time, assuming they were driven by, the propagation was driven by the seismic waves, and we are able to locate the earthquake in 2 minutes without any seismic data with 30 kilometers accuracy. So internet is the digital nervous system of our planet, and people are now real-time seismic sensors. So we have these 3 crowdsourced detections. So we look at the traffic on our website, activity on Twitter, activity on our app. What do we do with this? We do an app, which is called Lastquake. That's the snapshots of the app. And it is based on the assumption that the only earthquake of interest are the felt earthquakes. So the only earthquake of interest for the public are the felt ones. So we use this crowdsourced detection to identify the felt earthquakes. And you see on the left, we just use a very simple color code which reflect the expected impact of the earthquake. Just to give you an idea, felt earthquakes represent only 5 to 7% of the earthquakes we seismically locate. So that's very minority. And the Glassquake clearly targets eyewitnesses. If you look on the right, we have replaced the traditional online questionnaire where people answer questions to explain whether small objects have felt, etc., that we use to evaluate the level of shaking or damage. We have just replaced this questionnaire by a set of cartoons, and you just have to click on the cartoon. We know your location, and we know the local shaking level. And we also collect geolocated pics and videos and comments, and videos and pics being for the damaging earthquakes. The coverage we have is global, except China, because the people do not have access to the stores. The number of users is always between 1 to 1.5 million, basically, but it changes with time. I will go back to this. A better view of the usage is here, the cumulated app launches of our app over the last few years. So it's a heat map. So the bright area, that's where we have a lot of connections. So 3 months ago, Morocco was less bright than it is today, but it is really changing with time. And you see that we have a global coverage. So more precisely, how does it work? So suddenly we detect people launching the app. What we will do, we will automatically publish the information on our Twitter bot, so a bot which publish information on Twitter, on our website, and on our app. And we'll just publish earthquake possibly felt 2 minutes ago in, and we put the name of the area, and we ask the people from Twitter to go to our website. If you go on the website or the app and you click on the banner, so possibly felt earthquakes, you will fall on the cartoons, and you will be able to report your felt experience. As soon as we get an earthquake, the earthquake magnitude and location, we will associate the seismic information with this detection, and it will become, like on the right, like the 4.1 in Mindanao, so it will change. What is very important to understand is that we do not notify the crowdsourced detection. So we have an increase of the website or the traffic on our website. We publish this, but we do not send a notification on the app. So that's only the people who open the app at this time who will see it. We only notify once we get the seismic location, once the detection has been confirmed by seismic data. Just to show you, to illustrate the power that social media can have to drive people on our website, here it is a crowdsourced detection that we did in Indonesia. So we put GEMPA because GEMPA is the local name for earthquake, so to ensure findability of the tweet. The tweet is geolocated at the detection location, so if someone make a geographical search, you will find also this tweet. And this tweet attracted 2 million views, while we had at the time only 15,000 followers on Twitter. So you reach much larger audience that that the number of people who follow you. And if we look the impact in terms of activities on our website, nearly 80% of the people from Indonesia who hit our website in the 30 minutes following the quake had clicked on the link from the tweet. So basically, they were coming from Twitter. We are not able to know how many of them provided a felt report, but we know that we have an unusually high rate of felt report collection from the website. Normally, the majority are collected by the app. So this is a very powerful tool to drive people from the from Twitter to our collection tools. Now I'm going to show you in practice how it works with the app. So here on the left, you have so it is for an earthquake, a small magnitude earthquake below Athens. So here you have each black dots, black triangles represent the location of one of our app users. And you will see the number at the top of each of the figures will represent the number of people launching the app. And on the right, the number of people providing a felt report, and we'll see how it happens. So here we are 10 seconds after the quake. These are the 2 seismic waves, so what the people feel. We detect, so we are just 18 seconds after the quake. We have here 35 people who have launched the app. So that's the orange square. So we know something has been felt in northern part of the city. We don't know anything about the earthquake. 30 seconds, we have already 200 people who have launched the app. You see that now we are seeing it is over the whole city. We have already collected 4 felt reports. Here we are 1 minute after the quake. We still don't have the earthquake location. We have 700 people who have opened the app. And if you look, you don't see on the left, you don't see any propagation anymore. So you see that the earthquake has been only felt basically within the city. So you know it's not a big magnitude earthquake, otherwise you will see the effects of wave propagation. So we know it's not a big one. And if you look on the right, you see that so first that the level of shaking which is reported is always limited, so it's not high shaking, but the higher values are to the north. So we don't know whether the earthquake, where exactly the earthquake is, where the epicenter is, but it is very likely to be in the south part of the city. So it's probably on the north. We are 1 minute after the quake. We are not using any seismic data. We keep going, 3 minutes, 4 minutes. And finally, after 8 minutes, 9 minutes, we get the earthquake location from seismic data. So it is a magnitude 2.9. This is the star that I represent here. So very small magnitude earthquake. But basically, we had already all the information. We knew it was a small magnitude earthquake. We have basically all its effects through the felt reports we have collected. So basically we had little information missing. And if you compare at the end of the day for this earthquake, we collect 1,400 felt reports. So 80% of them were collected before the seismic information was available. So it's extremely fast, and it really provides a lot of information about the effects of the earthquake. But the last quake system is not an app. Is not only an app. It's not only an app because people install an app after the earthquake. So typically, this is the typical curve of the number of users that we can have after in a given region. People will install the earthquake after the main shock. Every time you have a felt aftershock, so you will have increase. And after over a month, people will start to disinstall it if there is less earthquake activity. This is typically, for example, what we had in Morocco following the devastating earthquake of last month. We had 4,000 users in Morocco at the time of the quake. 2 days later, we had 60,000 additional ones. So the app is not always the best to collect the testimonies, the felt reports for the main shock. You also need to have a website. Here, this is an example I like. It was an earthquake at the border between Wales and England. Of course, nobody knew about EMSC at the time because the level of seismicity in the UK is very low. We detected nothing on the app because nothing at the app, nobody has the app. Or whether people make Google search, a number of them hit our website. So we detected a traffic surge on our website. We published unconfirmed felt earthquakes in Wales and England. Please confirm. In a country where we are totally unknown, we collect 3,000 felt reports in 30 minutes. And the color here may not be you see that in green, that's the number of them that we have been collected through the app. The role of the app is minor, simply because nobody had the app at the time. So depending on the situation, the app or the websites will have a different function and can be very important. And it can change extremely rapidly. This is an earthquake in Albania, so magnitude 5.6. We collect 400 felt reports in 5 minutes, mainly from the app, but 400 in 5 minutes, remember this. 30 hours later, we have a 4.4. It is basically 50 times smaller, so much, much smaller in terms of energy. And we collect 1,000 in 5 minutes. So what happens is that in the meanwhile, people have installed the app. So it is a fully dynamic system where the people install the app very rapidly and may disinstall it after a while. What is also nice is that we don't only detect earthquakes, we detect everything that the people believe is an earthquake. So for example, we detect sonic booms. So every time you have a military plane breaking the sound barrier, people report it. We had one a few months ago in South France, and very often it is the same pattern. So it is along the coast. So basically the plane has just a bit too close to the coast. So you have all the people reporting just along the coast. If I make a radio or TV program and I mention the name of the app, you will have instantaneously some people downloading it and opening it, and it will make a trigger. So it is also funny to see the geographical audience of the programs you are in. We can detect explosion. I mentioned here Beirut. So the people, you remember the dramatic explosion in Beirut. People in Beirut knew it was not an earthquake, but it made all the windows rattling in Cyprus. And of course, in Cyprus, nobody knew it was an earthquake. So people reported their experience in Cyprus as if it was an earthquake. We have also detected a meteor, so entering the atmosphere above Croatia. And the example I showed you is something which puzzled us for a moment. So here it is something that happened in India, in Punjab. So for comparison, I put on the right the typical website traffic evolution after an earthquake. So you see a very sharp rise time. So it goes very fast. At the same scale on the left, that's what we have observed. So you see we have something which is which takes much longer to rise. So we detected it. We had also a lot of traffic, and we didn't collect any felt reports. So people were looking for information. They were coming from India, and we didn't collect any felt reports. And we are very puzzled. So I published this on the social media, and we also checked on the seismic sensors. There was no signal. So we are very puzzled. And I was approached by a colleague of us from India, and he found the answer. There had been a rumor there will be an earthquake at this time of the night in the area. So all the blue dots are the location of local newspaper which had reported there will be an earthquake in this area at this night. The open circles are the people who opened the app, so that you see that people were really expecting the earthquake, and because it was not coming, they were checking on the app whether it has occurred or not. So you see a lot of things, and you can see the way the people react and the way the people behave in this case. So the first part was about how last quake system works. Now is how can we use it for improved risk and crisis communication. The timeliness of prevention info messages is absolutely key. This is a tweet which was published by a flight attendant before the COVID. I think it will not work today. I think we won't observe it today. So they are just taken off, and there was a technical issue. So you had all the mask falling down. And the attendant, you see the complaint because they say, yeah, you don't listen to me when I explain the security, and you just, all of you put the mask wrong. It should cover both the nose and the mouth. So what's the point? What's the problem? What does it illustrate? It illustrates the problem of timeliness of the information. When you jump in the flight, you think about the meeting you are going to or the vacation you are going to. You are not really thinking about the possibility of an accident. So this is really the efficiency of the message depends on its timeliness. And smartphones is the only tools which can provide the right info at the right time at the right person. So we have to use it to improve risk and crisis communication. After the earthquake in Nepal, we made an online survey to our users, and we asked them, what do you want as an improvement? And they told us very clearly, we want to know what we should do after the quake. So we have introduced safety tips and safety checks. So safety tips is what should I do after the quake? And safety checks is just a pre-formatted SMS message that we prepare and that people can send to their loved ones or not send to inform them that they are safe. So in practice, every time we have a strong earthquake, we identify the people we have been affected by strong shaking. So and they receive a specific notification where we will have these do's and don'ts. So what should I do? What should I avoid to do? After an earthquake, I insist, it arrives a few minutes after the quake, so that's after the shaking. And we try to explain if there are cracks in your house, just leave it, go on open area, only call emergency services for serious injuries, use texto rather than phone calls because phone calls overload the network, and stay tuned. We have tested them. It's not easy to test this, to have something which is understandable in all the world, but we have tested them, so they are not perfect, but we had more than 800 answers, so we know it works pretty well. We are doing also the same for the tsunami, so we explain on the right that if you see some sea level change, if you hear a strong noise, if you are close to the sea and you have a very strong shaking, do not wait for a possible alert, just escape. And if you escape, it is easy. You have to go uphill, to take vertical evacuation, and you have to remain there because tsunami are very long, can be very long and can last several hours. So don't go down immediately. Why do we use visual communication? Because we work at global scale, and we have tried many years ago to work in multilingual, and it's very tricky. I don't speak Hindi, but I don't think it is the exact meaning of the translation here. So even some basic stuff you can make really big problems. So visual communication is also easier to grasp when people are under stress than verbal communication. So the other way we do for communication, we have a Twitter quake bot, so a bot which publishes on Twitter. I will not go full in details here, but we have more than 300,000 followers. And the idea is to provide information about all the felt earthquakes, but we discriminate between the type of earthquakes. So for example, destructive earthquakes will have a different number of tweets. You are not going to, you have to be focused on the actual impact on what the people may expect. But if I take, for example, the earthquake I presented in Athens, 2.9, it is an earthquake which had no damage. It doesn't create any damage, but it creates a lot of attention. And you know it creates a lot of attention, what we call the audience, simply because we collected a lot of felt reports. So in this case, this type of earthquakes open what we call what is called teachable moments. So moments where people are listening to your messages. So they're absolutely key to try to tell to the people, well, it was a warning shot, but be sure that you know how to behave in case of a stronger one. So we use all this type of information to provide educational tweets, explain how we work, and also to fight misinformation, which is becoming something which is more and more important. The Twitter bot, it's not only a bot. I also answer all the questions, especially when there is a damaging earthquake. I'm behind my screens answering the questions. And every time it is absolutely essential because it helps us identifying the recurring information needs. So basically, you have the same question appearing approximately at the same time after a damaging earthquake, systematically. And if it is recurrent, then you can make the answer fully automatic. So this is something that we have been doing. So this bot is always evolving. We have something like 55 now possible different tweets that will or will not be published depending on the cases. And when you make communication, then you can have misinformation. You may remember in 2018, there was an earthquake sequence close to Mayotte. Mayotte is a French island in the Mozambique Channel, so between Mozambique and Madagascar. It started in May with a magnitude 5.8, which was widely felt in Mayotte and well recorded because it's strong enough to be recorded all over the world. And it was followed by a lot of smaller magnitude earthquakes. At this time, we didn't know the reason, we didn't know the cause, but the most problematic aspect is that there were very few seismic sensors in the region, so we were unable to locate the earthquake. So the people were sending us felt reports and were unable to providing them what is the earthquake, where it is, etc., which led to many rumors, fake news, and were basically associated to conspiracy theories. We didn't want, but we wanted, we were. And we realized that we should be very careful with this because it can be very misleading. Just for a little story, we now know that the earthquake sequence is due to the emergence of a new volcano, which has just with lava just spilling over the seafloor. Again, this information is not new. This is a picture I recently collected from Laurenti, who is a specialist of historical seismicity. And this is a postcard on the left, which is said to be from Menton after the 1887 earthquakes, and it is not. It is just from Italy in Belluno in 1873. So this information is not new. Of course, now we see it more because of the social media, but again, it is not new. And one of the worst, really that's something we are really fighting is earthquake prediction. So I insist, we are totally unable today to predict earthquakes, which means where and when an earthquake will hit. And in 2019, there was an earthquake prediction, which was propagated on social media and by some media in Albania. And it led to the panic evacuation of the capital city of Albania. And you see here, that's the people evacuating the city. So hopefully there were no accidents, but this type of rumor can be deadly. So it is really something that we have to take care of. And you see, that's the type of answers we are providing. Do not listen to this, etc., etc. So now we try also to what is called pre-bunk this information. So when there is a damaging earthquake, like again the Morocco earthquake, you can be 200% sure that the following day there will be one guy, and I have to say I don't know any case where it is a female, so that's really a male issue, visibly, the prediction. You have one guy showing up and saying, oh, I had predicted it. And so now we pre-bunk it, so we say before it, don't be surprised, you will hear some people telling they had predicted. It's not true, and we explain why. We rely on different type of information. We also publish this during the teachable moments, so when there is interest by the population about earthquake activity. But I think it's also raised the question about the role of seismologists. Until recently, but I'm happy to see that it's changed, we are really the only one to take to really discuss this with the public directly. There are a number of reasons that I will not explain here, but we are really the only one. It started to change. Following the earthquake in Morocco, there were a number of my colleagues going in the newspaper, writing articles to explain this. And it is also changing because for the first time we have been invited to a TV program to discuss misinformation, which propagates on the social media. So I think it is really changing, and I think that's, as in all fields, it is something that we have to deal with. So I'm now switching to the last part, how this crowdsourced data can improve rapid impact assessment and in turn the efficiency of response, which rely on impact assessment. So I remind you the way the last quake works. So basically we have an app, we have Twitter bot, we have websites. We engage with eyewitnesses by providing what they are looking immediately after an earthquake, which is rapid earthquake information. And we collect, so these felt reports through the cartoons, geolocated pictures and images. So I will show you now how it worked for the Turkish earthquake, so back in February. So every time someone visits our website, we'll see a flash at the location of the visitor, and we will see how it evolves with time after the quake. So here it is. So we are in the middle of the night. Here, so we have people who are not sleeping visibly, and we are visiting our website. So that's random. Random. Here we are just after the quake. So we have the PNS seismic waves. So what the people feel. You see that they have generated a number of visits. We detect these visits. We have this crowdsourced detection. We are 70 seconds after the quake, and we located at the place of this green hexagon. We publish it. We say possibly felt earthquakes in southeast Turkey. Please confirm. And we are so 70 seconds after the quake, and we'll see now how fast we start to collect felt reports. So we resume. So you see immediately we start to collect them in Cyprus, and then from the epicentral region. We still don't have the earthquake magnitude and location. 5 minutes after the quake, now here, we have the first seismic evaluation, 7.7. Now we notify the public. So all the reaction you see in the Balkans is not because the people have felt the earthquakes, as people react to the notification. We are, and you will see, so all the dots, color dots, are the felt reports we collect. The scale is at the bottom, and basically we are 30 minutes after the quake, and we have collected 5,000 felt reports in the middle of the night. So the question is, what can we do with this? The first thing we can do is very simple, is just to evaluate how the level of damage and shaking evolves with the epicentral distance. So here, each of the blue dots represent individual felt reports. You have the epicentral distance at the bottom and the level of shaking or damage in the y-axis. So you see at the given distance, the reports are extremely variable, but when you make very simple statistics, you draw this red curve, which is extremely precise. The uncertainty is smaller than the thickness of the curve. And you see that within 70 kilometers of the epicenter, we have intensity 8, which is characterized by moderate to heavy damage. In Turkey, for this type of level, we expect 0.1% fatality rate, which means that with 3 million people, we know in a data-driven approach that we have at least 3,000 fatality. So we know it's a disaster. And we know also that it is a strong, very strong underestimation. Why so? Because an earthquake is a rupture. When you have a magnitude 7.8, you expect a rupture which is 150 kilometers. So we are not a point source. It is something which has much larger extension. So we know we are probably exceeding the 10,000 fatalities. Within an hour, we have this information, and it is data-driven, it is not model-driven. So how can we use it otherwise? We can, the way classically the impact is estimated, we compute first what is called shake map. Shake map is the spatial distribution of the level of shaking or damage. And from this, you will then cross with the exposure and evaluate the impact. Here, this is something done with our colleagues at the US Geological Survey. we inject our felt report in the shake map to provide constraints. And here, what is represented is the uncertainty with and without our data. So without our data on the left and with our data. And you see that this data dramatically improved the shake map. It is for the Petrinja earthquake in Croatia in 2020. So this is the first way another way also to use them. If I go back to the earthquake in Turkey, on the left, you have a map, which is the level of damage and shaking determined by our colleagues in Turkey. And the black line that you see is the rupture. So that's where the seismic rupture occurred. So the first thing you see, it is the seismic rupture which controls the spatial distribution of the damage. If you don't know where the rupture is, you cannot map the damage. And this is the problem which was observed after this quake. So when you locate the earthquake on the right, what you get, you have the epicenter. The epicenter gives you where the rupture starts, where it is initiated. But even if you know on which fault it is, so you know the orientation of the fault, which was the case in this case, in this example, you don't know whether the rupture moved to the north, moved to the south, or was bilateral. And of course, because the rupture geometry controls the spatial distribution of damage, it makes some dramatic change in the impact assessment. So what we have been doing with our colleagues at ETH in Zurich, they have developed a software which is in operation in the US and which normally use dense accelerometric network. So when you have one sensor every few kilometers to determine the rupture rapidly to improve the estimation of the impact. So normally you plug the system in, you plug the accelerometric data in the system and you find a line model which best fits the observation. We have just replaced the accelerometric data with the felt reports. And here, this is the geometry that we on the right. This is the geometry that we have obtained after only 10 minutes after the quake. So after 10 minutes after the quake, we were seeing that Antakya was probably hit hard, something that it was not clear for quite a while in this case. We knew also it was another or few thousand fatalities, we underestimate, because we also collect geolocated peaks. And despite the fact that there has been some major communication issues, because in Turkey, in this area, the cell tower were installed on buildings. So with a lot of buildings collapsing, you had a lot of issues for the communication network. Still, we have collected pictures. I showed just the one at short distances and showing damages. And you see, for example, this one at the bottom, it is 175 kilometers in Alep. So in Aleppo, from the epicenter, so much more than the 70 kilometers we have estimated, and we see total collapse. So we knew that we had severe damage at much longer distances than the 70 kilometers average that we have observed. So we knew we are definitely much far worse than we had expected. So here, this is just to show you. So on the right, on the left, sorry, it is figures from a recent paper by our colleagues from the SGS. So this is the time scale from the earthquake occurrence, how fast they were able. So just focus on the figures in the middle. That's basically the fatality estimate. So I've just put the values. In the first hours, the best estimate was number of fatalities between 100 to 1,000. The same 4 hours after the quake. For the estimate to be above 1,000, they had to wait 2 days, and their final estimate took 6 days. So what were we able to do at the same time? I will go back to the first one. I have not explained it yet, but I will explain it later. But we had the final rupture in 10 minutes. We knew in 1 to 2 hours that we were far more than 3,000 fatalities. We knew that locally the intensity was much greater than moderate to heavy. And I will also explain it later. We detected also landslides 12 hours after the quake. So this is just to compare without any specific treatment what we're able to say. So how it could speed up the evaluation. But now what we are finalizing, again with the USGS, so on the left, this is the final fatality estimate at the bottom, so the histogram, using the actual fault rupture as observed by satellite. So it took 6 days to have this. After 6 days, they redo the whole shake map computation and fatality estimate. They find the best scenario was between 10,000 to 100,000 fatalities. We compare now, we just inject the fault reports that we had in the first 10 minutes. We have a scenario between 1 to 10,000. And if we inject also the rupture model that we have determined in 10 minutes, we get the same evaluation that they did after 6 days. So really the crowdsourced data can dramatically, so basically having a reliable impact fatality estimate after 10 minutes rather than 6 days, which can make a difference for mobilizing the rescue operations. And another things that we have been doing with our colleagues at GFZ in Germany. So knowing that the magnitude 7.8 is impactful is not a big challenge if there is population around. What is more challenging is when you have just a handful of fatalities, like for this earthquake in Japan, for death, simply because all the evaluation we do are statistical. And when you have only a handful, we are not in the statistics. We are just driven by individual accidents. The second also very difficult cases are the moderate magnitude earthquakes, so magnitude around 6, typically the one that we can expect in the mainland France. It will impact within a dozen of kilometers around its epicenter. The problem is that first, our location uncertainty as location at global scale is typically of the same order, about 10 kilometers. So if you have a city and the earthquake, you cannot be totally sure whether it is below the city or just at its edge. The depth of the earthquake will have also dramatic impact. And we had this earthquake last year in Afghanistan, which killed more than 1,000 people and which remained below the radar for several hours. So what we have been doing, we have used artificial intelligence. We have taken all the earthquakes for which we had fault reports within 10 minutes. We take only the first 10 minutes, and we have explored the spatial-temporal dimension of this data set to evaluate the probability for an earthquake to be impactful by just using the fault reports available in 10 minutes. So the model is the color, so that's the probability of being impactful. And when you have the numbers, that's the earthquakes which have not been used to calibrate the model. So you see the E11, that's the Japanese earthquake. You find it in the red area. So basically in 10 minutes after the few fault reports we had, we knew it was probably an impactful event. The earthquake E10, so that's the Afghan one, you see it was also close. So this is something which is still ongoing, but what we are looking for is really to have a traffic light system. And within 10 minutes to be able to say, this is definitely not an earthquake of any concern. Oh, here we may have some impact, better to stay tuned and to gather more information. Or here this one is definitely impactful. We have to make proper damage estimate. So we also detect landslides. So we have developed a system with the Qatar Computer Research Institute and British Geological Survey. So the idea is pretty simple. We collect all the tweets containing the keyword landslides, mudslides, and associated in different languages, and having a picture. Then we have trained an artificial intelligence tool to recognize pictures which are actually related to landslides. It's throughout 99% of the tweets. And here, this is the landslides that we detected after the Turkish earthquake. So we detected it 12 hours later, but remember that the earthquake was at night, so you cannot expect to detect it much faster. Unfortunately, We are running now in big problems with Twitter. The policy has been changing. We have wasted a lot of time trying to follow. They change their mind every other day, so it's a bit difficult. We hope we will be able to resume it, but it's unclear. So now we have already started to work on messaging apps. So we have released the Telegram bot for rapid information and crowdsourcing, and we'll do the same for WhatsApp. So the few takeaways that we like to remember, first of all, eyewitnesses, all the data for rapid impact assessment. Without them, without the data collected by eyewitnesses, except if you have dense axionometric network, the impact assessment can only be extremely uncertain. We have all the tools to do it. There is no technical issues to do it, but people are not providing information to you to please you. They provide information because first you have satisfied their needs. So you have to understand the needs of the people. You have to understand what they expect. You have to provide them with what they expect to engage with them and for them to start providing some data. There is no single tool doing all. We use crowdsourcing, social media harvesting, artificial intelligence, statistics. So we have really to explore all the different avenues. And this is not only a theoretical development here. We are part of the Aristotle Consortium. It is a European consortium, and we provide rapid impact assessment of disasters within the EU and outside the EU to the ERCC. The ERCC is the 24/7 unit of the European Civil Protection Unit. And we provide this in 3 hours, so we contribute for the earthquake impact assessment. So this work has been done by a large number of people, first the EMSC team, but also a lot of collaborators, outside collaborators. And I also, again, want to thank the SCOR Foundation for Science, which has been extremely useful for us to bring us to the next level. Thank you.